Usually when we talk about making a map, there's this expectation of permanence.
Oh, sure.
Like
Right.
you survey the land, you draw the coastline, and the cartographer just points at the parchment and says, there it is. That's where the ocean ends.
Right, it's fixed. And, I mean, it's comforting. We really like our boundaries to be stable and reliable.
Yeah, exactly.
Right.
But then you step into the world of cosmology and mapping the universe, suddenly that map isn't on a flat piece of paper anymore.
No, not at all.
It's drawn on the surface of a balloon that is actively inflating. And the invisible air pumping into that balloon, just stretching it faster and faster, well, honestly, it's a complete mystery.
It is the absolute definition of cosmological muddy waters, truly.
So for decades, we've thought of the universe's expansion as being driven by a constant, unchanging force called dark energy. Einstein's famous cosmological
The
constant.
famous lambda.
Yeah. But what if we've been wrong? What if this force is actually changing over time? Or, maybe even more unsettling, what if gravity itself works differently on a cosmic scale than it does right here on Earth?
It's a massive question. And the reason we're asking it today is because we're looking at some incredibly fresh, genuinely disruptive data.
We really are. Our stack of sources today for this deep dive includes some bleeding-edge astrophysics research from 2025 and 2026.
Yeah, it's super recent stuff.
We're looking at the explosive data release 2 results from the Dark Energy Spectroscopic Instrument, or DES, as it's known.
Yep, DESI.
And we are pairing that with a really fascinating January 2026 preprint by theoretical physicist Zakaria Sacker, which proposes a totally new way to test modified gravity using literally the biggest telescopes humanity has ever built.
Right. So our mission today is to figure out why the standard model of cosmology is suddenly in absolute jeopardy, what this new effective dark fluid theory actually is, and how a tag team of 2 megatelescopes might finally solve the mystery of the dark universe.
Okay, let's unpack this, because before we get into the new stuff, we really need to establish the baseline for you all listening. Because to realize why the astrophysics community is currently having a collective panic attack.
Which they are.
Yeah, they really are. You need to understand what normal used to look like.
Right. The normal you're referring to is what physicists call the ΛCDM model. It has been the absolute bedrock of cosmology for, over 20 years now.
It's the standard.
Exactly. In this model, the universe is made of about 5% regular matter. That's the stuff that makes up you, me, the Earth, the stars, everything we can see.
Just 5%. That always blows my mind.
It's wild, right? Then there's about 27% cold dark matter, which is the invisible gravitational glue that kind of holds galaxies together.
Right. And the remaining 68%.
That is dark energy, the famous lambda.
Right. And lambda represents a cosmological constant, the key word there being constant.
Precisely. It is supposed to be an unchanging property of the vacuum of space itself. Like, think about normal matter or light. As the universe expands, that matter gets diluted.
Sure, the space gets bigger, so the stuff inside it gets spread out.
Right, exactly. But dark energy doesn't do that. As the universe expands, the density of dark energy stays exactly the same.
Which is so weird to think about.
It is. It creates this steady, uniform, repulsive pressure that pushes everything apart. It's an elegant mathematical concept. It fits most of our old data beautifully. And, Einstein actually proposed the math for it over a century ago.
Right. But then, in 2025, DESI dropped an absolute bombshell.
Oh, it's huge.
DESI is this incredible instrument in Arizona that maps the universe by measuring something called baryon acoustic oscillations, which honestly sounds like something straight out of Star Trek.
It really does.
Like, how do we actually use those to map anything? What even is a baryon acoustic oscillation?
Okay, so you can think of baryon acoustic oscillations, or BAOs, as basically frozen sound waves from the very early universe.
Wait, sound waves? In space?
Yeah. Well, shortly after the Big Bang, the universe wasn't empty space. It was this incredibly hot, dense soup of plasma. And sound waves actually rippled through this cosmic soup, physically pushing matter around.
Okay, so like ripples in a pond, but made of superheated plasma.
Exactly. But as the universe expanded and cooled, that plasma eventually turned into neutral atoms.
And when it cooled, the sound waves did they just stop?
They froze in place, just instantly. They left these faint spherical rings of slightly denser matter all over the universe.
Oh, wow.
Yeah, and over billions of years, galaxies preferentially formed along those rings because there was slightly more matter there to begin with.
That's incredible. So we can actually see these rings today.
Yes. And because we know exactly the physics of how big those rings should be, we can look at the distribution of millions of galaxies today and use those rings as a highly precise cosmic ruler.
Ah, I get it. By measuring how big the ruler looks at different distances, we can track exactly how fast the universe has been expanding over billions of years.
You nailed it. That's exactly how it works.
That is wild. We're literally using the acoustic echoes of the Big Bang as a tape measure.
It's one of the coolest things in astrophysics.
But, and here's the kicker, when the DSI team looked at their data release 1 and data release 2, measuring these frozen sound waves across millions of galaxies and quasars, the data didn't perfectly fit a constant dark energy anymore.
No, it didn't. The ruler didn't look the way ΛCDM said it should.
The results were, like, striking, right?
Very. And they didn't just look at DSI in isolation. They combined the DSI data with measurements of the cosmic microwave background, which is the afterglow light from the Big Bang that actually captured the image of those frozen ripples initially.
Okay.
And they also added data from exploding stars, or supernovae. When you put all that together, they found a significant tension with the standard model. Depending on exactly which data sets you combine, that tension sits between 2.5 sigma and 3.9 sigma.
And just for context, in physics terms, 3.9 sigma means there is less than a 1 in 10,000 chance that this is just a random fluke in the data.
Right. It's not a confirmed discovery yet. We usually wait for 5 sigma for that. But it's a massive red flag.
So the universe is trying to tell us something. Our math is wrong somewhere.
Yeah. What the data is pointing to is that dark energy might be dynamical, meaning its density isn't staying the same. It appears to actually be decreasing over time.
Decreasing. And this is where the sources get into some deeply weird physics. Because the data shows that between a redshift of 0.5 and 1.5, which is basically looking back in time between, 5 and 9 billion years ago?
Roughly, yeah.
Right, so looking back then, the dark energy equation of state shows a decreasing trend. And it crosses what physicists call the phantom divide.
Oh, the phantom divide, yes.
I want to pause here because the phrase equation of state can be really dense.
Really?
What does that actually mean in plain English?
Okay, so the equation of state is usually labeled with the letter W. In physics, it's a way of describing a fluid by taking the ratio of its pressure to its energy density. Let's use a physical analogy.
Please do.
Imagine a closed cylinder of steam, like in an old steam engine. If you pull the piston back and expand the cylinder, the steam spreads out. The density of the steam drops and the pressure drops.
Right. That makes total sense. That's just basic thermodynamics.
Exactly. But dark energy isn't steam. For a true cosmological constant, W is exactly -1.
-1.
Yeah. In our cylinder analogy, if you pull the piston back to expand the space, the density of the dark energy inside stays exactly the same, but it exerts a negative pressure. It actually pushes outward on the piston on its own.
Okay, so that's the baseline.
Yeah.
W equals -1. But crossing the phantom divide means W drops below -1.
Yes. And that is what the DSI data hints at in certain epochs.
Which is mind-bending, because if W drops below -1, it means the energy density of the dark energy is actually increasing as the universe expands.
Which is crazy, right?
It totally defies all basic intuition about how stuff dilutes when space gets bigger. It's like imagine stretching a rubber band, but instead of the rubber getting thinner and weaker, the rubber magically gets thicker and pulls harder the further you stretch it.
That's a perfect way to visualize the phantom divide. You're getting more energy out of literally nowhere as the space expands. The rate of acceleration isn't a flat line. It is evolving and potentially tearing the fabric of reality apart faster and faster.
But wait, I have to push back here.
Go for it.
Before we start completely rewriting the laws of thermodynamics, how do we know we aren't just looking at this the wrong way? What if the dark energy is totally fine and it's perfectly constant, but our measuring stick is bent?
Ah.
Like, couldn't our fundamental understanding of gravity just be slightly off?
You've just articulated the exact debate that is fiercely dividing astrophysicists right now. Are we looking at a new, changing substance filling the universe, which is often called quintessence, or are we seeing the absolute limits of Einstein's general relativity? Are we feeling the presence of a new modified gravity on massive cosmic scales?
It's a massive crossroads.
Yeah.
But why is it so hard to just test if gravity is different? Can't we just look and see?
Because modifying gravity gets incredibly complicated, incredibly fast. General relativity is mathematically incredibly tight. We know it works. If you tweak how gravity works on cosmic scales to explain the DESI data, you run the massive risk of ruining how it works right here in our solar system.
And if Einstein is wrong locally, then things like the GPS satellites in our phones, which rely on the time dilation equations of general relativity, shouldn't work correctly.
Exactly.
The existential stakes for physics are just huge here.
Precisely. You can't just slap a patch on gravity without causing ripples everywhere else in the math. So to figure out if it's dark energy changing or gravity changing, we need a completely new mathematical net to catch the truth.
Which brings us to the January 2026 paper by Zakaria Sacker. Theoretical physicists realized that tracking all the different ways modified gravity could warp the universe was becoming a statistical nightmare.
Oh, a total nightmare.
It was like trying to keep track of 100 moving targets at once. So Sacker proposes a highly generalized parameter. He calls it the effective dark fluid equation of state, or a fear.
What's fascinating here is how brilliant this approach is. It takes modified gravity theories and basically encapsulates how they affect both the background expansion of the universe and the growth of large-scale structures.
Because gravity really has two jobs on a cosmic scale, right?
Right.
It dictates the overall stretching of the universe, pushing things apart, but locally, it dictates how matter clumps up inside that stretching universe to build massive galaxy clusters.
Exactly. Usually modifying gravity means you have to track multiple moving parts separately. Sackers mathematically rolls up 3 distinct parameters into one single elegant variable.
The sources mention these 3 parameters explicitly, and they sound intimidating, but let's break them down. First, there's the Newtonian potential parameter called mu0.
Right. That essentially measures how much matter pulls on other matter. It's the standard gravity we feel, the force that dictates the physical motion of planets and galaxies.
Just regular old gravity pulling stuff together.
Exactly. Second, there's the gravitational slip parameter, eta 0.
Gravitational slip, that sounds, what is slipping exactly?
This one is fascinating. It measures the difference between how gravity affects the movement of slow, massive objects like galaxies versus how it bends massless light.
But wait, under standard Einstein gravity, there shouldn't be a difference, right?
Right. In general relativity, there is absolutely no slip. Mass and light are affected the exact same way by the curvature of spacetime. If we measure the universe and find that eta 0 is not 0, it means light and matter are feeling gravity differently.
Which would be huge.
That would be an absolute smoking gun that general relativity is incomplete.
Wow. Okay, and the third piece of this puzzle is a redshift-dependent Hubble parameter, H0 background, which just tracks the overall background expansion rate of the universe over time.
Right.
So, Sacker takes matter, pulling on matter, gravity's effect on light and the expansion of the universe, and rolls them all into one metric.
Yep.
It's kind of like looking at someone's single credit score instead of combing through their entire financial history of every individual coffee and grocery purchase to see if they are a financial risk.
That's a great way to put it. It's the composite index of modified gravity. It simplifies the model.
But I'm stuck on something here. By mashing these 3 complex variables into one parameter, aren't we losing crucial details? Doesn't that make it harder to spot tiny deviations from the standard model? If you blend red, blue, and yellow paint together, you don't get a sharper picture, you just get a gray blob.
That is exactly the intuition you should have, and it's a completely valid concern. You do lose the specific fingerprint of which parameter is causing the anomaly.
Okay, so you wouldn't know why it was failing.
Right, you wouldn't know immediately if the slip was off or if the Newtonian potential was off. But here is the mathematical payoff that Sacker's paper demonstrates. Projecting these 3 parameters into the single parameter actually improves the bounds of our constraints by about 30%.
Wait, it makes our theoretical tools 30% sharper? How? If we're blurring the details.
Because of something called degeneracy.
Okay.
When you try to measure 3 incredibly subtle parameters at once using telescope data, the statistical noise and the uncertainties kind of bleed into each other. If one parameter moves a little, it might look identical to another parameter moving a little.
Oh, I see. So you can't tell which one is actually shifting.
Exactly. By funneling the theoretical modeling to us, you reduce the degrees of freedom, you stop letting the math wander around. It sharpens the theoretical focus so that if any deviation from standard cosmology exists, it is statistically much easier to spot that initial crack in the foundation.
Okay, that is incredibly clever. But having a brilliant new equation on a whiteboard is completely useless unless you have the physical data to plug into it.
Naturally.
To test Growler to see if gravity is actually slipping, we need to look at the sky in ways we literally never have before.
And that requires machines that, frankly, border on science fiction.
Here's where it gets really interesting. Our sources highlight 2 heavyweights, that are teaming up to test this 2026 theory. First, there's the SKA, the Square Kilometer Array.
Ah, the SKA. It is an absolutely colossal radio telescope project. We are talking about thousands of dishes and up to 1 million low-frequency antennas spread out across deserts in South Africa and Australia.
1 million antennas.
1 million. It is designed to measure radio waves, specifically mapping the distribution of neutral hydrogen gas across vast cosmic epochs.
I want to pause on that. How does looking at a bunch of invisible hydrogen gas tell us anything about whether Einstein was wrong about gravity?
Because hydrogen is the raw material of the universe.
Yeah.
It's the scaffolding. Where the hydrogen gas clumps together, that tells us exactly where gravity is pulling the hardest. By mapping the neutral hydrogen, the SKA is essentially mapping the invisible gravitational skeleton of the universe.
Oh, that makes total sense.
Yeah, and if modified gravity behaves differently than standard gravity, that skeleton is going to look structurally different.
Got it. And joining the SKA in this tag team is Euclid. Euclid is an incredibly advanced European Space Agency telescope currently out in space. It doesn't look at radio waves, it measures optical and near-infrared light.
Right, visible and infrared.
And it is mapping an astonishing 14,000 square degrees of the sky. What is Euclid's main job here?
Euclid's superpower is measuring the shapes of billions of galaxies to look for weak gravitational lensing, as well as precisely measuring how galaxies cluster together.
Weak gravitational lensing, that's when mass bends light, right? Like looking through a funhouse mirror.
Yes. Even though we can't see dark matter, we know it has mass. So when light from a distant background galaxy travels toward our telescopes, it has to pass by huge, invisible clumps of dark matter.
Right.
The gravity of that dark matter literally warps the fabric of space, acting like a lens that subtly distorts the shape of the galaxy behind it. Euclid is so precise it can measure those tiny, tiny distortions.
So we have SKA looking at radio waves from the hydrogen scaffolding, and Euclid looking at the visible and infrared light to see how the funhouse mirrors of dark matter are distorting things.
Exactly. Two entirely different ways of seeing the cosmos.
But the paper gets really dense when it talks about how they actually combine them. What does it mean when the source talks about combining radio continuum probes with photometric clustering?
I know, the jargon is super heavy there. Think of it like taking a radio picture of the universe with the SKA and a visible light picture of the universe with Euclid.
Okay, two pictures.
Individually, each picture has static or, systematic errors. But when you overlay them, when you cross-correlate the radio continuum data with the optical photometric data, the true signal aligns perfectly.
Oh, and the random static from the individual telescopes just cancels itself out.
Exactly. The noise drops away and the actual structure pops out.
Okay, that is the synergy. And Soccer's paper breaks down exactly what happens when you use this overlaid method to hunt for modified gravity using the new torometer. Let's look at the forecast they ran.
Sure.
Imagine a mock universe where modified gravity is real and it deviates from standard ΛCDM by about 10%. In this scenario, equals negative 1.03.
Right. Close to -1, but noticeably off. Now, if we only use the next stage data from the SKA survey to look for this 10% deviation, the math shows we only get a 1 sigma detection.
And for anyone who isn't a statistician listening, 1 sigma in the world of physics is essentially nothing.
It's nothing.
It's statistical noise. You could just be looking at a smudge on the telescope lens. You'd never claim a discovery on 1 sigma.
Never. You'd be laughed out of the room. But when you combine the SKA data with the upcoming Data Release 3, or DR3, from Euclid, utilizing that cross-correlation we just talked about, the detection improves from 1 sigma to roughly 2 sigma.
Wow. That's a huge leap in confidence.
It is a massive improvement. It proves mathematically that cross-referencing these completely different observational methods amplifies the true signal of the universe far better than either telescope could ever do alone.
But, and there's always a but in astrophysics, even with that leap, the sources lay out a pretty sobering reality check.
They do. It's a tough pill to swallow. The realistic conclusion of the 2026 paper is that even with the 30% mathematical improvement from using the dollar parameter, and even with the unprecedented synergy of SKA and Euclid teaming up, distinguishing this generalized modified gravity from standard ΛCDM at the sub-percent level is going to be incredibly difficult.
Right. A 2 sigma detection is tantalizing. It makes you raise your eyebrows. But it's not the 5 sigma gold standard that physicists need to definitively declare that general relativity is officially broken and go collect their Nobel Prizes.
Not even close. The forecast shows that to truly rule out the standard model, or to prove the specific flavor of modified gravity, we are going to need data from even more advanced stages of these surveys. The current and near-future data will give us strong hints, but definitely not the final word.
So what did this all mean for us? I mean, it means the universe isn't giving up its secrets easily.
No, it is fighting us every step of the way.
Think about it. We are building the most advanced, sprawling, complex machines in human history. We are pointing them at the sky, crunching the data with entirely new mathematical frameworks like Roller, and the universe is basically saying, you're getting warmer, but you're not there yet.
It's a profound testament to how incredibly successful Einstein's theory of general relativity has been. It is so hard to find a genuine crack in it. But, the DESI data from 2025 has given us the first real scent of blood in the water.
Which brings us right back to our map. If you are listening to this, you are living through a unique moment in human history. We thought the map of the universe was fixed. We thought dark energy was a constant, steady breath inflating the balloon.
We really did.
But the 2025 DESI data showed us the balloon is being pumped erratically. And now, in 2026, scientists have built a mathematical net, and they are teaming up the SKA and Euclid telescopes to find out if the fabric of the balloon itself, gravity, is fundamentally different than we thought.
If we connect this to the bigger picture, there is one more concept hidden in our sources that completely flips this entire search on its head.
I'm ready. What is it?
Okay, so we've been talking about looking at the deepest, furthest, emptiest parts of the universe to find out if gravity behaves differently.
Right.
But what if modified gravity is hiding right here, like right under our noses?
Wait, we established earlier that we know general relativity works perfectly in our solar system. The planets orbit exactly how Einstein predicted.
They do. But the sources mention theories with things called screening mechanisms. They have fantastic names, by the way, like the chameleon mechanism or Weinstein screening.
The chameleon mechanism. That sounds like it's in disguise.
That is exactly the physical mechanism at play. These are mathematical theories where a fifth force of gravity exists, but its behavior is heavily dependent on the density of its environment.
Okay, so density matters.
Huge matter. In incredibly dense regions of space like inside a galaxy or right here in our solar system, this fifth force becomes incredibly heavy and sluggish. It effectively screens itself.
Meaning what? We can't detect it.
Right. It becomes mathematically invisible, mimicking Einstein's standard gravity perfectly.
So we can't see it when we look at the planets orbiting the sun because the local density of the sun forces it into hiding.
Exactly. The density essentially suppresses it. But when you travel out into the vast, empty voids of deep space, where the density of matter drops to almost zero,
The chameleon sheds its disguise.
boom! The field becomes light, and this fifth force runs wild, driving the accelerated expansion of the universe that we observe as dark energy.
That is astonishing.
Isn't it?
It means the laws of physics aren't universally wearing the same face. So the provocative thought we leave you to mull over today is this. What if the fundamental forces of nature actively disguise themselves, depending on exactly where you are standing in the cosmos?
It's a haunting thought.
What if the ink, the paper, and the very rules of geometry change depending on which part of the cosmic map you are trying to read?
It absolutely changes how you look at the night sky.
It really does. You aren't just looking at stars, you're looking at a universe that might be actively hiding its true nature from us. Thank you for joining us on this deep dive. Keep looking up and keep questioning the universe around you.